Hi everyone, welcome back. Today we're going to be talking about the trapezoid rule. And here's a problem we're posed. So we have this curve. It's pretty arbitrary, right? And we're tasked with estimating the area underneath it. So, back in Calc AB, we looked at this using rectangles, right? So what I would do is I would draw a rectangle here maybe, and go up and I'd draw a rectangle here, and one here as well. And I'd go ahead and sum all those up, and that would give me a good estimate for the area underneath the curve. But what you might have noticed is that a better way of doing it would be to use trapezoids. So if I do the same thing, I'll pick out a few points equally spaced, as best as I can draw them at least, along my curve here. And I'm instead going to connect them with trapezoids here. That was not well drawn. Here, here, and there. Because we know that rectangles have to remain horizontal when you connect the lines. But with trapezoids, let me put one more in here. With trapezoids, the tilt can follow the curve more closely, right? So what we're going to do then is we're going to add up all of the area of these individual trapezoids. We remember that the area of a trapezoid is equal to the average of the two bases times the height or the width of the triangle, or sorry, the trapezoid. And then really what we need to specify here is the number of trapezoids we want to use. So let's call this trapezoid 1, trapezoid 2, trapezoid 3, all the way up to trapezoid n. And let's give the points on the curve that I use names as well. Let's call this one y0, y1, y2, y3. All the way up to this point here is yn. And then there's a simple formula for figuring out the width of each of these trapezoids. We'll call delta x. The simple way of finding that is you simply take the length of your interval, b minus a, and divide it by n. So n can be 10, n can be 100, and that will give you, how evenly spaced far apart they are. Okay, so this is the problem we're trying to solve. And what we're going to do is we're going to derive a formula because, it might be boring, but I find that there's merit in doing so. So let's go ahead and find the area of trapezoid 1. We know from the formula this is 1/2 times the average of the bases. The base right here is this line and this line here. Okay, so this is going to be y0 plus y1, and then we already know that they're evenly spaced, so the height is going to be delta x. Okay, let's do the same thing with trapezoid 2. We get 1/2. Now my base is y1 right here again, and y2. So I just moved over 1. So I have y1 plus y2. Again, the height is delta x. Let's do one more. We get 1/2. It's going to be y2 plus y3. If we follow this pattern, we can keep doing this all the way up to the nth trapezoid. Let me do lowercase n. This is 1/2. Now I have this one right here, which is the second to last height. So we denote it yn minus 1. And then I have yn as my final base here, plus yn, and again, delta x. And remember, we're supposed to add all of these up to find the actual area of the interval. So what I can do is I can, see what they have in common. So my area of the entire thing, I'll say it's a total. They all have a 1/2 out front, and they all have this delta x. So I can make this delta x over 2. And then now I have to look closely at all the terms involved. So I have a y0 from that first trapezoid, but notice I have two y1s. So I have plus 2y1. I also have two y2s. So I have plus 2y2. I'd also have plus 2y3 if I had done that, right? So I'd have this y3 from that trapezoid, and then I would use y3 as the base for trapezoid 4, right? So I'd use it here for trapezoid 4 as well. And so you can see the pattern here. This continues all the way up until plus 2yn minus 1, where I would use it here and also in the one before it. And then finally, the very last thing is I add on a singular yn because I only need it once with my last trapezoid. Okay, so this is the formula we have. I hope that made sense because really now that you have this formula, that's all you're going to use. You're never going to have to set it up like this again. but I think there's merit in figuring out where it comes from as opposed to just writing it down. Okay, so let's do an example. Let's go ahead and estimate the area underneath a curve. So we're going to denote that as the integral from 0 to pi sine x dx using, right, so I have to tell you how many trapezoids, 4 trapezoids. Okay, so we have our formula from above. There are a few things we need to know, right? We need to know this delta x, which we said how to find, right? So I take the length of my interval, which is going to be pi minus 0 divided by the number of trapezoids I have, which is 4. So I have pi fourths. And then I need to know as well all of these y values here and here and here. So I'm going to make a table where I have x here, and then I have sine of x, which is going to form our y's, I should say. Okay, so I start out at 0. That's the beginning of my interval. I end at pi, and my delta x is pi over 4. So I add pi over 4 to 0. I add pi over 4 here. I add pi over 4 again. And I end at pi, and you'll note that we have exactly 4 trapezoids, which is perfect. Okay? And then you'll remember from basic trig that this is 0, this is root 2 over 2, this is 1, this is root 2 over 2, and this is 0. Okay? That's literally everything we need, right? So I have all my y's, I have my delta x, so I can say that my area is going to be equal to pi over 4 times a half, so that's that 1/2 that we have out front here. And then literally sum up all of the things. So I have 0 plus 2 times root 2 over 2 plus 2 times 1 plus 2 times root 2 over 2 plus 1 times 0. So you get pi eighths times 2 plus 2 root 2. If you do that math out, that would be exactly equal to, not exactly equal to, about equal to 1.896. We know the actual area to be 2, so this is approximately 5% error. So considering that I can estimate the area underneath a very difficult function, sine of x, to within 5% using just 4 intervals, that's pretty nice. One thing to think about is I could have told you immediately that I knew this number was going to be less than 2, no matter how big n was. So that's something to think about as well. It has to do with the function we're using, right? It's not going to be true in every case. But this begs the question, this is 5% error. What if I want to get down to 1% error? Then do I just, keep increasing this to 5 and 6 and 7 and 8? The answer is there's actually a formula we can use to figure out if I need to get below a certain error, how many subintervals do I need to use? I think this is one of the coolest parts of Math 104, so we're going to go through it. I'm going to just give you the formula. I don't think there's merit in deriving it, but we have this. We have the error of the trapezoid rule. It's given E sub t as the error of trapezoid rule. You can bound it from above, which means we have a maximum value for it, of this m b minus a cubed over 12n squared. Okay, so we know b, we know a, we know what n is, or we're solving for n if we're given e. But we have this mysterious m up here. M is defined to be the maximum value of f double prime of x on the interval a to b. Okay, so that looks, sorry, I have an extra absolute value bar in here. It looks a little complicated, but it's really not that difficult. Okay, so let's do an example. It's going to essentially come down to finding the maximum value of a second derivative, and also just, knowing how to compute something cubed. It's really not going to be too difficult here. And there's always going to be some sort of shortcut we can use. Okay, so let's estimate the minimum number of subintervals. So those are n, required to approximate I should have wrote this down beforehand, but it's too late now. Approximate this from 2 to the 4, 1 over x minus 1 squared dx to within 0.01%. Okay, so that's a pretty narrow margin, right? I need it to within one part in, what is that, 10,000? Yeah, one part in 10,000. So, your boss is really adamant you get this down pretty close to exact. All right, so we literally plug everything in. 1 part in 1,000 is our error. So 10 to the minus 4. I have to be a little bit below that, right? So my m, I'm going to keep just as it is until we solve it. And then I have, sorry, this is going the wrong way. I can have at maximum 10 to the minus 4. So I need to be below that. I have m, I have 4 minus 2, right? So that's the length of our interval here, 4 minus 2. And then I have over 12n squared. We're solving for n, so let's go ahead and move everything to the right side. I'll get n squared is greater than or equal to m times 8. Let me go ahead and just do that. 8m over 12 times 10 to the minus 4 on the bottom. So I'm going to make that times 10 to the 4 up top. Cool? Okay, so the very last thing we have to do is solve for m. We said m is a max value of 2 derivatives of my function. All that's left to do is to recognize that the stuff in your integrand is your function, which you probably would have guessed. So my function here is 1 over x minus 1 squared, which I find to write, or easiest to write in this form when I'm taking derivatives like this. So my first derivative will give me minus 2 x minus 1 to the minus 3, and f double prime will give me 6 x minus 1 to the minus 4th, which now that I'm plugging values in, I'll write it like this. Okay, so here's a common pitfall of Math 104. At this point, we're looking for a maximum value of the second derivative, right? So back in Calc AB, what we would do is we take a third derivative, is something, we set that equal to 0 to find the maximum and the minimum, right? We do some sort of test, we check the endpoints. That could take a lot of time, and you could fall into that on an exam. What we're going to do instead is we're going to look at this function. We know it's going to be decreasing or increasing exclusively within this interval. So what we know about something over x is that it's going to look something like this. Okay, so that's really all we need to know. If it looks something like that, and there's no singularity in our interval, which there isn't, right, because we're outside of that 1 value, then I know that my function here, this is my f double prime, is going to hit here at 2 and then be constantly decreasing. So now right off the bat, my maximum value m is going to occur when x is equal to 2. So that tells me that m is equal to 6 over 2 minus 1 to the 4th, which gives me 6. Okay? So what I can do now is I can plug that back in. I'm running a little bit out of room, but I get n squared is greater than or equal to 48 over 12, which is 4 by 10 to the 4th, which tells me that n has to be greater than about 200 for me to get down to within 1 part in 10 to the 4th. Okay? So, that's a lot of subintervals. I personally would not want to be the one subbing it all up using this formula. But we at least know that that's how many we need, and we don't need to keep going one by one from 5 to 6 to 7 to get this down. So I think this is one of the most important parts of Math 104, the error estimates involved in the trapezoid rule. So I hope this was a good